As an example, I'll share a situation I encountered while buying a car. The salesman wanted me to pay extra to have my tires filled with nitrogen gas instead of compressed air. The reasoning was that as the weather changed and got hot or cold, the pressure in the tires would change. His claim was that nitrogen gas would not change pressure as air would. Let's first use the ideal gas equation of state to estimate the mass of the gas in the tire. Then we will compute the change in pressure corresponding to different temperatures. First, we define our system as the gas within the tire. Assuming there are no leaks, this is a closed system. The only interactions with the surroundings that can occur are work and heat. Assuming that the volume of the tire does not change, the work interaction is eliminated, and we are left with only heat. Applying my favorite form of the ideal gas equation of state, we can compute the mass of gas within the tire. Pressure times specific volume is equal to the specific gas constant times temperature. We can recast this form in order to calculate the mass by substituting the definition of specific volume. Specific volume is 1 over the density. Density is mass divided by volume. Thus, specific volume is volume divided by mass. Also, we can compute the specific gas constant using the universal gas constant and the molecular weight. The form of the ideal gas equation of state becomes pressure times volume divided by mass is equal to the universal gas constant divided by the molecular weight times the temperature. We can solve this equation directly for the mass of gas in the tire. Mass is now equal to the pressure times the volume times the molecular weight divided by the universal gas constant times the temperature. An average tire has a volume of 10 liters. We can convert this to cubic feet. 1 liter is 0.0353 cubic feet. The volume of our tire is 0.353 cubic feet. The universal gas constant, R bar, is 1545 feet pounds force per pound mole degree Rankine. The molecular weight of air is 28.97 pounds mass per pound mole. And the molecular weight of nitrogen is 28.01 pounds per pound mole. Let's assume that the tires were filled to a pressure of 33 pounds force per inch squared on a day that was 70 degrees Fahrenheit. As with temperature, we must also use absolute pressure when multiplying or dividing. When a tire is filled, the pressure is measured by a pressure gauge that references local atmospheric pressure. Thus, the 33 pounds force per inch squared pressure that the tire is inflated to is actually a gauge pressure. To compute the change in pressure, we must convert to absolute pressure. Remember that pressure absolute is equal to the gauge pressure plus the atmospheric pressure absolute. Let's assume that the atmospheric pressure absolute is 14.7 psi. We calculate the absolute pressure in the tire is 33 psi gauge plus 14.7 psi absolute, which is 47.7 psi absolute. We can substitute these values into the ideal gas equation of state, which we already have solved for M. Pressure is 47.7 pounds force per inch squared. The volume is 0.353 cubic feet. The molecular weight of air is 28.97 pounds per pound mole. And we need to convert our inches into feet by multiplying 144 inches squared per foot squared. The universal gas constant is 1545 pounds force feet per pound mole degree Rankine, which gets multiplied by our absolute temperature, which is 70 plus 459.67 degrees Rankine. We find that the mass of air in the tire is 0.086 pounds mass. For 4 tires, this is 0.343 pounds mass. To calculate the mass of nitrogen that would fill the tire, we substitute the molecular weight of nitrogen. The result is that the mass of nitrogen in the tire is 0.083 pounds, which for 4 tires is 0.331 pounds. Now, let's compute the change in pressure for the tire on a hot and cold day. Once again, we assume that the volume of the tire does not change. This is a reasonable assumption because a tire does not stretch much as we inflate it. The tire simply changes shape. So we will assume that volume is constant. We apply the ideal gas equation of state. Pressure times specific volume is the specific gas constant times temperature. Remember that specific volume is the volume divided by the mass for a substance whose density is constant throughout the system. Because we are assuming that the volume does not change and that the mass is constant because there are no leaks, we can recognize that the specific volume is constant regardless of the temperature. Solving for the specific volume, we find that specific volume is equal to the specific gas constant times the temperature divided by the pressure. What we have now are 2 states. The state 1, where we filled it, and state 2, which is the condition that we're interested in after the temperature is changed. At state 1, the specific volume is equal to the specific gas constant times temperature 1 divided by pressure 1. At state 2, the specific volume of 2 is equal to the specific gas constant times temperature at 2 divided by pressure at 2. As noted above, specific volume of 1 is equal to the specific volume of state 2. We can equate the other side of the equation for state 1 and state 2. The result is that RT1 over P1 must equal RT2 over P2. The specific gas constant is the same for both, and so it cancels. Note that R, the specific gas constant, is the only variable that contains information about what substance is filling the tires. So now we are left with T1 over P1 is equal to T2 over P2. We can rearrange to yield a final result that relates the change in pressure to the change in temperature. P2 over P1 is equal to T2 over T1. We can see that as the temperature changes, the pressure will change as well. There's no dependence on which substance is in the tire because the R is canceled. Therefore, the claim that nitrogen will not change pressure as air does is false. Let's compute the change in pressure for a cold day in which the atmospheric pressure is 0 degrees Fahrenheit. Remember that when we multiply and divide temperatures, we must use the absolute temperature. So T1 is when we filled the tire at 70 degrees Fahrenheit, which we convert to Rankine, the absolute temperature, by adding 459.67 equals 529.67 degrees Rankine. Temperature 2 is 0 degrees Fahrenheit, which we convert to Rankine by adding 459.67, and we just arrive at 459.67 degrees Rankine. Substituting this into our solution, we can calculate that P2 over P1 must equal 459.67, that's temperature 2, divided by 529.67 degrees Rankine. The Rankines cancel and we're left with a unitless number, which is 0.868. Once again, we must use absolute pressure when multiplying and dividing. So P1 absolute is equal to 33 psig plus our atmospheric pressure, 14.7 psia, which is 47.7 psia. We can then substitute that into our relationship and find that on the cold day, the absolute pressure is P1, 47.7 psia, absolute, times 0.868, which equals 41.4 psia. We can convert this result to gauge pressure by subtracting the local atmospheric pressure. .4 psia minus 14.7 psia. So our gauge pressure is 26.7 psi gauge. So we've dropped from 33 psi down to 27 psi. On a cold day, the pressure in the tires can be much lower than when they were filled on a warm day. If you were to add air in the winter to maintain proper tire pressure, be sure to let it back out as the weather warms up or your tires will be overinflated. As an exercise, imagine that you fill your tires to 33 psi gauge on a cold day in which the temperature is 0 degrees Fahrenheit. What would the pressure be if the weather warmed up to 70 degrees Fahrenheit? The answer is 40.26 psi gauge. That concludes the example. Thanks for tuning in and have a great day.